Hi, welcome to Dissolved Chemistry. So let us continue our discussion on this equilibrium. In the previous videos of equilibrium, we have discussed equilibrium established in various physical processes, that is solid, liquid, liquid gas and solid gas, and followed by that equilibrium established in dissolution of solid in liquid and gas in liquid, and we spoke about Henry's law in detail. Okay, in the present video we will start our discussion on the chemical equilibrium. Okay, so equilibrium established in a chemical reaction, we call it as what? Chemical equilibrium. What all those aspects we will study in detail in this video. Okay, chemical equilibrium. Okay, so prior to defining the term what is chemical equilibrium, let us consider one general reaction. Okay, say for example A plus B combines reversibly to give C plus D. What do you mean by reversibly? A plus B have the tendency to combine to give C plus D. Similarly, C plus D also have the tendency to combine back to give A plus B. So then we call it as what? Reversible we call. Okay, so as the reaction starts, consider that you got with 1000 number of molecules of A and B you have taken in the reaction vessel. Say for example, we will take a reaction vessel where what we have done. So we have taken 1000 molecules of A, 1000 B we have taken, and we are allowed to interact with each other. And you consider that what happens, and it will be at time is 0 second you take, right? So now what happens as the time progresses from 0 to 10 seconds. Okay, so what we will see is 10 seconds. Then we will be finding 900 molecules of A are there, 900 molecules of B are there, and then obviously 100 molecules of C plus D are going to form. Okay, and what does it implies? In 10 seconds, 900 means 1000 to 900 it has reached, meaning is what? So therefore, per second, 10 molecules have been converted or combined, A and B, 10 molecules have combined to give C plus D, it implies. Okay, so now we will see here A plus B, with what rate they are going to combine? See here, okay, they are going to combine with a rate of 10 molecules, okay, per second they are going to combine. Okay, so in the meantime, anyhow we don't have C plus D initially, so therefore 0 are there initially, and after 10 seconds what happens here? Already 100 C and 100 D have been formed after 10 seconds. So now slowly what happens? C plus D also start combining back to give A plus B with a rate of, say for example, it is happening with 2 molecules per second. Okay, 2 molecules per second initially it happens after 10 seconds. Okay, up to 10 seconds nothing has happened, after 10 seconds it also starts. But the rate of combination of A plus B is what? 10 molecules per second. And rate of recombining back C plus D into A plus B is what? 2 molecules per second. And it goes on. And let us see after 20 seconds what happens. Okay, it's an hypothetical example. Okay, just for illustration I have taken. So 800, say for example 200 are there. Okay, so now the rate of combination, now the concentration of C plus D has increased now. So obviously what happens? This rate will rise, say for example 3 molecules. Now what happens? It may come down to 9 molecules per second now. Okay, so slowly the rate of forward reaction goes on, decreases as the time progresses, and rate of backward reaction goes on, increases. And there is a time, okay, say for example at 30 seconds, say for example, so you have 700 each of A plus B concentration, and C plus D is 300. And similarly when we reach 40 seconds, we found that it is around 600 molecules of A and 600 molecules of B, and 400 each, what? Your products are there. Okay, so now you see here, after reaching this, when I observed at 50 seconds, it was found that it is remaining 600, and it is remaining as 400, say for example. So what is the meaning of this? the concentration of A plus B and C plus D both are remaining same and they are not changing with the time. What does it imply? See here, as the time progresses and after certain interval of the time, what happens? The rate of forward reaction, say for example, 5 molecules are being converting per second, means 5 molecules of products are being converting into reactant. Reactant 5 molecules per second and product also 5 molecules per second. So therefore net change in the concentration of A and B is 0. Okay, there is no change in the concentration. What is the reason for that? Rate of forward reaction has become equal to rate of backward reaction. When rate are becoming equal, then there is no net change in the concentration of the reactants and the products with the time. And that situation we call it as what? Chemical equilibrium. Okay. So when the concentration remains constant with time, no change in the concentration, then we call it as what? Chemical equilibrium. And as the reaction establishes an equilibrium, then whatever the concentration of the reactants and products are found, and those concentrations we call it as what? Equilibrium mixture. Okay. So the concentration of the reactants and products at equilibrium is called as equilibrium mixture. Okay. So now let us define. I think you have understood what is the meaning of this. So means as the time progresses, reactants convert into product. Initially no product was found, and after reaching a certain interval of the time, what happens? Rate of forward reaction and rate of backward reaction becomes equal, because initially rate of forward reaction was high, rate of backward reaction was too low, and a time arrives where what happens? Rate of forward and rate of backward becomes equal, and that situation we call it as what? Equilibrium. Okay. And the concentration at equilibrium we call it as what? Equilibrium mixture we are going to call it. Fine. Let us define the term chemical equilibrium. Reversible reaction when the rate of forward reaction becomes equal to rate of backward reaction, then that state of reaction we call it as what? Chemical equilibrium. Okay, so that we call it as what? Chemical equilibrium. So therefore A plus B combining to give C plus D reversibly, C plus D. So at equilibrium, okay, the rate of conversion of A plus B to C plus D and C plus D to A plus B becomes equal. Fine. So that we will see graphically. Time coordinate you can take. This you consider as time, and this is concentration coordinate. Okay. So now we will take. Initially the reactants will be at what? High concentration. Say for example 1000 each, we have taken 1000 A plus 1000 B in the example we have taken. So now what happens as the time progresses and your C and D at time 0 interval. Okay, so this is 10 seconds, this is 20, 30, 40, 50, 60, 70 we will take, right? So now as the time progresses, the concentration of the reactant goes on decreases. Okay, decreases. Similarly, with time what happens? The concentration of the product goes on increases. Okay, and after reaching a certain point, so both what happens? Run parallelly with the time. Concentration, okay, remains constant. You see here. Okay, if we extrapolate like this, so you can see that the concentration of the reactant and the products, what they are doing, they are remaining constant. Okay, so that we call it as what? Now here we call it as what? At 40 seconds, it has attained an equilibrium, and after this, the concentration of the reactant as well as product, okay, this is product, reactant, this is product, okay, both are not changing with respect to the time. Meaning is what? Already the reaction has attained an equilibrium. Initially, the concentration of reactant decreases, concentration of the product increases, and after a certain point, after reaching that, what happens? Rate of forward and rate of backward reaction becomes equal. So then what happens? Your reaction is said to be at equilibrium, and after that time, what happens? There is no net change in the concentration of the reactants and products is observed, and that concentration of the reactants and products at equilibrium, we call it as what? Equilibrium mixture. Okay, remember that one. Is called equilibrium mixture. Equilibrium mixture. Okay, so that is referred as what? Equilibrium mixture. You should remember these points. Now, is this equilibrium is dynamic or static? Dynamic meaning either after attaining the equilibrium, either reactants are converting into product or products are converting into reactant or not. So that question arises. Of course, the equilibrium is said to be dynamic. Okay, dynamic means there is a continuous conversion of reactant into product, product into reactant. But it happens with the same rate. Because of that reason, we cannot change or we cannot visualize. Okay, so the change in the, because concentration is not changing with respect to the time after attaining an equilibrium. So therefore, we feel that as if it is static, but it is not like that. Dynamic it is. How to understand that it is a dynamic? Okay, so we will illustrate that dynamicity of the equilibrium with one example. Okay, chemical equilibrium is a dynamic. To understand that, we will take an example of formation of ammonia. Okay, so it is being done. Say for example, it is a very important, industrially important reaction. Okay, that is N2. 1 mole of N2 combines reversibly with 3 moles of H2 to give 2 moles of NH3. Okay, with the evolution of heat. It is an exothermic reaction, negative it is. Okay, so make a note of this. Now, how this reaction occurs? Okay, graphically we will see this one, and then we will see the experiment which is being used to explain the dynamicity of the reaction. Okay, our equilibrium is dynamic. So now you take, this is the concentration axis, fine, and this is your time axis, right? So initial concentration of highest is your hydrogen, because we are taking 3 moles. So therefore we will take here, and we will take nitrogen here. Okay, and your ammonia somewhere, it is initially it is 0. So therefore we will take here. Okay, so as the time passes, then what happens? The concentration of the hydrogen goes on decreases. Okay, decreases, and it attains an equilibrium. Similarly, the concentration of the nitrogen also decreases. This is your N2 and this is your S2, and similarly the concentration of the ammonia goes on increases and attains an equilibrium. Okay, so this we call it as what? Equilibrium. At equilibrium, what you will be finding? Ammonia is there, hydrogen is there, and dinitrogen is also there. Now, how to come to know that it is a dynamic? So now, suppose if we carry out this reaction in the reaction vessel, okay, in a closed vessel, you can take N2 will be there at equilibrium. Equilibrium mixture comprises what? N2, H2 and NS3. To understand the dynamicity, what it is being done, instead of taking a hydrogen, we have taken a isotope of hydrogen, that is deuterium. Okay, and in another reaction vessel, it is being carried out to get ND3. The deuterium, it is an isotope of hydrogen, you should remember that. So now it is carried out in another vessel, and it will also attain an equilibrium. Okay, so at equilibrium we will be finding equilibrium mixture contains N2D2 and ND3 as the components, right? Now what you do, you take to check that it is dynamic, you mix both the equilibrium, one which is taken with hydrogen, one which taken with deuterium, both are mixed together, one mixed together. Okay, so two things we will see when both are mixed. So if equilibrium is dynamic, then what we are expecting, and if it is not dynamic, then what we are expecting, that we will see. Okay, after mixing, if it is not dynamic, static, if your equilibrium is static, we expect that the reaction mixture should contain N2, D2, H2, NH3 and ND3 we were expecting. Okay, so but as it is dynamic, what means what are the components you will find in the reaction vessel, and this we check with mass spectrometry. Okay, so we are going to confirm this with mass spectrometry. We are going to get N2, D2 is there. Okay, so then H2 is also there, and we will be having ND3, NDH2, okay, ND2H, okay, apart from this DH we have. Okay, so like this the components were found in the what are equilibrium mixtures. So it indicates that so there is an exchange of what reactant into product, product into reactant, that is going to be indicated by these products. Okay, or if it is static, we were expecting this, but as it is dynamic, we are all getting all these things at as an equilibrium mixture. Okay, so this confirms the dynamicity of a chemical equilibrium. Okay, I hope you have understood. So what do you mean by chemical equilibrium and its dynamic nature? Okay, reaction when it attains an equilibrium, if it is attaining an equilibrium, that is only possible when the products have the same tendency to give the reactants, or have the tendency to convert into reactants and reactants into product. Then only equilibrium is possible, or it is going to attain an equilibrium. Now, suppose if I start the reaction with the product instead of reactant. Say for example, you take so H2 plus I2, a reaction reversibly combines to give hydrogen iodide. Okay, so this is what is the reaction. Or you can take, say for example, N2 plus 3H2 reversibly combined to give 2 moles of NH3. Now, my question is that if I start the reaction with ammonia or reaction with hydrogen iodide, is going to establish an equilibrium with at the same instant or same concentration? Of course, it is going to attain. Either you start the reaction with the product or start the reaction with the reactant, your equilibrium concentration will be always a constant for a given reaction under given conditions. Okay, so then we will see that one. Say for example, we will consider this combination of H2 plus I2 to give 2HI. Okay, so let us graphically and try to understand this one. Try to remember that either you start the reaction with the reactants or with the products, the equilibrium concentration of the reactants and product will be always constant under given set of conditions. Okay, so now we are starting with H2 plus I2 to give HI. And similarly, if you start with HI, 2 moles of HI, okay, reversibly give H2 plus I2, okay, right? So we'll take like this. H2 plus I2, I will illustrate by values, then we will take back as graphically we will represent this one. 2HI gas. So now say for example, I have taken 100 initially, 100 molecules of S2, 100 molecules. This is an hypothetical, okay, it is not relevance with any practical values what we get, okay. So this is 0 at the initial state, okay. So this maybe you take at a time 0 second. So then at 10 seconds, I will be finding 90, 90, then it is 10. Okay, so then at 20 seconds, you find this 80, 80, then it is 20. So they, for example, 30 seconds you take, this is 70, 70, and this is 30. So at 40 seconds, okay, it reaches to 60, 60, say for example 40. And at 50 seconds, you find that 60, 60, and 40, means at this point, okay, so this is the point where what has happened, the reaction has attained an equilibrium, we can say. Similarly, what we will do, we will start with 2HI. Okay, suppose I am starting this reaction with what, 100 molecules of HI to give H2 plus I2, right? So we have started this reaction with 100 molecules, and then what happens, say for example, it is at 0 second, for example, you will be finding 0, 0. So then at 10 seconds, 90, then it turns out to be 10, 10. Okay, 80, 20, 20 you take. Okay, 20 seconds, 30 seconds, then what happens? It will become 70, and this becomes what? 30, 30. Okay, so then at 40 seconds, it will be 60, 40, 40, and at 50 seconds, okay, right? So you will be finding this as 50, and this will be 50, 50. Then what happens at 60 seconds? So it goes to 60, 40, and this becomes 60, 60, and after that at 70 seconds again it remains 40, 60, 60. So what does it implies? See here, the equilibrium concentration of HI and H2I2 at equilibrium. Okay, and here if you start with HI and if you start with H2 and I2, so then also we will find the same concentration at equilibrium. What does it indicate? It means that either you start with the product, either you start with the reactant, the equilibrium concentration always remains constant if your given set of conditions are maintained as a constant. Okay, so that important point you should remember regarding chemical equilibrium. Let us see this same thing in terms of graph. Okay, so then it will be very clear for you. See here, we will take time axis in both the directions, both we are going to plot. So this is the reverse reaction. Okay, so time we will take like this, and we have started this reaction with HI. Okay, here we have started reaction with H2 and I2. Okay, so as the reaction progresses, here your initial concentration of HI is here. Okay, here initial concentration of H2 and I2. Okay, so concentration axis, this is also concentration axis. So now as the time progresses, then what happens? The concentration of the reactant goes on decreases. Okay, so here concentration of the product goes on increases, right? And here, so we'll take little above. So here, if you start with HI, then what happens? So concentration goes on decreases and attains an equilibrium. So concentration of increases H2 and I2 and it becomes equilibrium. Okay, and the equilibrium concentration will be always same. Okay, either you start with HI or you start with H2 and I2, and this is applied for all the reactions which attain equilibrium. Okay, I hope you have understood three things. You should make note that at equilibrium, the chemical reaction rate in the forward direction and backward direction will be always same. And second point is the chemical equilibrium is dynamic, and that we have demonstrated with one of the example by taking a isotopic labeled that is hydrogen, that is deuterium we have taken, right? Then third important point is either you start with the reactant or with the product, your equilibrium is going to attain at the, or equilibrium concentration remains constant. Okay, is it clear? Either you start with the reactant or with the product. Okay, these are the three important points you should remember, and we will discuss in the upcoming video the law of chemical equilibrium and equilibrium constant we will derive. Okay, thank you for watching, and don't forget to subscribe our channel.